Hello, my name is Ahmed Al-Nahas, and I'm a PhD candidate at the Center for Turbulence Research at Stanford University. And this is the work that I've done in collaboration with Professor Perry Johnson from the Mechanical and Aerospace Engineering Department at Irvine on the enhancement of boundary layer skin friction by turbulence using an angular momentum approach. Transition and turbulence in boundary layers is important because it dramatically influences the drag on both blunt and streamlined bodies. For example, on blunt bodies, it allows the boundary layer to remain attached for a larger region of the object, reducing form drag. And for streamlined bodies, turbulence contributes to higher friction drag, which is important for aerodynamic applications. In particular, turbulence does this by increasing the wall normal transport of momentum and heat, and as well as causing the boundary layer to grow faster in spatial dimension. The net result of these two effects is a significantly higher skin friction, as seen on the plot on the right, where three different transition scenarios lead the laminar skin friction to rise to a much higher turbulent level. And our goal was to quantify the effects of turbulence on skin friction enhancement and relate flow features above the wall to the shear stress at the surface. Those features including turbulence itself, pressure gradients, as well as the growth of the boundary layer. This was done before for internal flows using what is known as the FIK identity by Fukagata et al., where you integrate the channel mean momentum equation 3 times, equivalent to a second moment of momentum around the channel half height, leading to a decomposition between the laminar and the Reynolds stress contributions to the skin friction coefficient based on the bulk velocity, as shown in the box in the middle. Notice that the Reynolds stress integral is weighted by its distance away, by the Reynolds stress value away from the wall. While this is applicable to internal channels or internal flows, once this triple integral is applied to boundary layers, it is no longer obvious what the laminar and the turbulent contributions are, because the laminar term becomes, or the viscous contribution in a general sense, becomes influenced by the mean flow distortion, and this decomposition is no longer easily seen. This can be seen from the different engineering contexts that we discussed when we look at internal flows and boundary layers. In internal flows, we care about the friction factor versus the flow rate, which is found by taking a second moment of the equation or a 3-time integral of the mean momentum equation. However, for boundary layers, what we care about is the skin friction versus the free stream velocity. And to relate these two quantities, we can take a first moment integral of the viscous term, relating, as you can see, the free stream velocity to the friction at the wall. And we can view this first moment as a torque that acts to distort the boundary layer profile, either to increase or decrease the skin friction at the wall. Now, in a channel, there is a geometrically imposed length scale around which to take this second moment, which is the channel half height. But in a boundary layer, this geometrically imposed length scale doesn't exist. So we introduce a yet to be determined length scale, which we call L, and we take moments around it. To do so, we start from the mean momentum deficit equation. And if we integrate once around about the wall, we end up with the von Karman momentum integral, but that does not include the direct effect of turbulence. It is embedded implicitly into the shape factor. However, if we take a first moment of momentum about this yet to be determined length L, we can decompose the skin friction into a Reynolds number dependent component, which we would call the laminar for, as will be shown, and a direct Reynolds stress effect plus other terms. Now, if we choose L such that the Blasius skin friction is equivalent to this 1 over Reynolds number, we would in fact succeed at accomplishing what FIK did for internal flows, which is decomposing the friction coefficient into a laminar friction isolated from all other contributions and a turbulent enhancement. But because we are now dealing with the first moment, our Reynolds stress integral is unweighted. This highlights the fact that our definition of skin friction depends on the engineering context, and therefore our decomposition should depend on the engineering context as well. If we do this to the full momentum deficit equations, we end up with these 6 terms at the top, which include the laminar, a direct Reynolds stress component, a component of or a torque dependent on the streamwise growth of this boundary layer, on the mean vertical flux, on the free stream pressure gradients, and on negligible bound terms that are usually neglected in boundary layer analysis. There are 3 new length scales that have to be introduced. One is an angular momentum length scale, which is an analog to the momentum length scale when L is when there is no moment taken about a length scale L. There's a vertical momentum thickness and an angular momentum thickness. And we've shown that by doing this, we've succeeded at decomposing the friction factor into a laminar, a turbulent flux, and all the other terms. This equation is consistent with previous existing decompositions or relationships, in the sense that when L goes to infinity, we recover the von Karman momentum integral equation, and it recovers the same properties of Fik for internal flows. Choosing L has a significant physical meaning, and that is the fact that different boundary layers can be compared at different Reynolds numbers. So when we want to compare a laminar boundary layer to a turbulent one, or a turbulent one under pressure gradient, we have to make the choice of which Reynolds number are we holding constant. So this L is an inevitable factor of this particular decomposition. And we show here 4 different choices of decomposing or choosing this L to get a decomposition at different REX, RE theta, RE delta star, or RE delta 99. And by making this choice, we specify the laminar boundary layer with which we're comparing the flow against. Given this new relationship, which we call the angular momentum integral relation, we proceed to analyze 3 different transitional scenarios, with 1 including natural H-type transition and 2 different bypass transitions subject to free stream turbulence. They're color coded with blue being the Wu database, the green being the Johns Hopkins, and the red being the H-type transition. If we look at the skin friction coefficients, transition occurs sooner in bypass cases, and the peak is smoothed out due to averaging in the span-wise direction. And we see a better collapse for skin friction when plotted versus RE theta, indicating that the flow has forgotten the particular transition scenario when things become turbulent. In the fully turbulent region, if we choose L to be the L that isolates the laminar contribution based on theta and normalize the contributions by the local value of skin friction, we see that the major contributor to this balance is the Reynolds stress, which in fact is approximately the total skin friction from all 3 different calculations. And the remaining non-negligible components, being the streamwise growth, the mean vertical flux, and the laminar contributions, balance out to 0. One potential question to ask is this collapse to 1 a byproduct of self-similarity with respect to RE theta? So we compute here the integrand of Reynolds stresses normalized by this length scale, and colors go from dark to light, indicating movement across higher RE theta values. What we find is that the integrand itself does not remain constant, which is expected. The Reynolds stress increases and moves closer to the wall as the Reynolds number increases. However, the integral itself remains constant. We further proceed to ask if this question, if this behavior is exhibited at higher Reynolds numbers. So we analyze a Reynolds number that is much higher using the recycled, rescaled turbulent boundary layer of Sierra et al. And we find that the relationships are approximately correct, but there is a mean trend with Reynolds number. And what we expect to be the case is that the boundary conditions impose slightly different behaviors that this particular relationship is sensitive to, meaning that we could potentially use this angular momentum equation for fine-tuning inflow turbulence generators. Since we are given a choice of what the length scale is, we've also analyzed the flow when we compare a boundary layer at the same REX. And in this case, we notice a very different behavior in which the Reynolds stress contributions and the mean streamwise growth of the boundary layer are the most dominant terms, and they are approximately balancing with their difference contributing to the skin friction, indicating that the growth in the streamwise direction when viewed from an REX perspective is much more important, highlighting the opportunity to choose how you define the boundary layer you're comparing against. We've also done this during transition because our decomposition or relationship is ambiguous to whether the flow is transitioning or not. And we can see that during transition, the primary contributor is a large peak in Reynolds stress that is offset by, in fact, a mean downward momentum flux due to the mean wall normal velocity during transition. And these trends that are seen in the H-type transition are simply, they exist, but they're muted due to the span-wise averaging across intermittent spots. So in summary, we presented a theory for decomposing turbulent skin frictions into a laminar and a turbulent contribution. And it is intuitive with an interpretation relating to torques around the point, and is relatively extensible. And the results show that the integral Reynolds stress is the dominant balance in boundary layers when viewed at the same RA theta, and that the streamwise growth and vertical flux heavily influence transitional boundary layers. Thank you very much for your time.